Hi and welcome to the Arctic. My name's Jamie and we are here on AXA XL Arctic Live. We're broadcasting from the UK Arctic Research Station and we are in Ny-Ålesund. And Ny-Ålesund is the northernmost permanent community in the world and it is very special. It's an international science village, so we have stations from around the world and a collection of scientists who are studying the atmosphere, the ocean, and the land and glaciers around us to find out how our incredibly wonderful Arctic but fragile region is changing. Now, today we are looking at ocean acidification, an incredibly important topic. We're going to do a couple of live investigations, and then later this afternoon, in a couple of hours' time, we'll be speaking to PhD student and polar oceanographer Hannah Green, and we'll be delving a little deeper into the topic. Now, I'm not going to tell you all about ocean acidification just yet because we're going to do a few things first. We're going to say hello to all those schools who are watching in the USA, Colombia, and Canada. Hi to you guys, and big shout out to INEM in Colombia. Hello to all the students there. A big hello to all the students at Riverside Public School in Canada. Hi. And also to those students watching at Union Point Academy in the USA. Wonderful to have you with us, and a big hello as well. Now, we're going to go outside in just a bit so you can have a look around. Then we're going to talk a little bit more about the theory of ocean acidification, and then we're going to do a couple of live investigations. Do follow along in the classroom and see if you can get the same results as us. And then we have time for a short Q&A at the end of the session. Now, we are here on a 2-week research expedition, and we are looking at two things. We are looking at ocean acidification and we're looking at marine plastics. Marine plastics is the focus of all our wonderful discussions tomorrow when we have live investigations too, and also the chance to talk to Dr. Kerry Lewis, one of the principal investigators of Arctic Live. And we're in the middle year of that last year, and then the final year of our monitoring next year. So let's have a little look outside and see where we have been taking our samples, because although there are lots and different ways of researching the Arctic Ocean, it's really important to get out into the field and find out exactly what's happening. So I'm going to grab my microphone, and Ellie behind the camera is going to follow me outside, and we'll go and see what it's all about. So here we are, coming outside into the wonderful wilderness, the great outdoors, and just looking here down from the UK Arctic Research Station, one of the most amazing views in the world for me. This is the fjord where we've been sampling, so the sea's coming in from that strait in between Svalbard, the island we're on between the top of Norway and the North Pole, and Greenland. There's a strait that goes through between those two, connecting the Arctic and the Atlantic Oceans. So that's the dark water where we've been. Out towards the back, the inner fjord, is where we spent our first few days sampling, dodging icebergs, temperatures with wind chill down to -25. And though it seems like that's not too far away, you can see the snout of the glacier. The snout's the name we give to the front of the glacier, that great massive ice moving from the interior of Svalbard down towards the sea. And that is a Kronebreen. That's 10 to 15 kilometers away. I'm about 15 kilometers from where we are at the moment, but it almost feels like it's in touching distance. So that sort of jaggedy blue snout carving off the icebergs coming off the front of that as the ice falls into the ocean. Now, even further away, we can see the peaks of the Tre Krona, the Three Crowns, and those are about 25 30 kilometers from where we are at the moment. And this is where we are on a little boat bobbing around and making sure we're finding out how the ocean chemistry, referring to ocean acidification, and looking at the plastic and the plankton as well. But we are not camping out on the sea ice this time as we were in 2011. We are based at a research station, and you can see a mass and jumble of buildings behind. As I referred to earlier, this is an international science community up here. We are staying at the UK Arctic Research Station, so we're very nice and toasty in our individual bedrooms. We have hot water, hot showers, lab space, a sitting room for doing the odd job, including preparing some of our work to put out some sample sites tomorrow. We also have plentiful supply of tea and biscuits to keep us going in the cold. Very, very important. We nearly thought we ran out of tea bags, which on a UK station, you can imagine, is a cause for great panic. And there was nearly a distress flare fired up. The UK Arctic Research Station has run out of tea, but no, we found some in a storeroom, so that is okay. The station is up and running again. But you can see behind there's a bit of a NASA facility that's going to be put up there. There's a power station in the background, there's store sheds, workshops, all that kind of thing. Because up here, although it looks like it's a sort of village, we are actually very remote. So to get here, and the flights just come in, we have 4 flights a week, 2 on Monday and 2 on Thursday. If I can just point back round, Ellie, those flights are coming on a sort of almost like a charter system. So those flights are only for people staying here, and that's coming 25 minutes over the centre of Svalbard from the main airport in Longyearbyen as the main settlement of about 2,500 people. And then to get to Svalbard itself, that's taking a 2-hour flight, 2.5 hours if you're coming up, or actually closer to 3 hours coming up from Oslo, or 2 hours from Tromsø. So we are remote, and if anything were to go wrong, it's sort of okay-ish because you can get a flight in or a helicopter in from Longyearbyen and then on by flight to the mainland. But if the weather comes in, we are very remote and can be incredibly cut off. So we'll just get back inside, and we're all wired up here because any wireless or Wi-Fi or Bluetooth signals interfere with the atmospheric research being done. And so, oh dear, that's a bit of a breeze out there, slamming doors in the Arctic wind. And come down back at the desk here. So just to think that further out to our north, that's looking this way out, directly out through the door. After you pass a couple of London houses and the harbour, there is nothing much except for a few mountains and glaciers before we reach the North Pole. We are at 79 degrees north, with the North Pole at 90 degrees north. But today is all about ocean acidification, and it's often known as climate change's evil twin, and it is concerning carbon dioxide as well. So let's start with where carbon dioxide comes from. It's a naturally occurring gas, but since the advent of the Industrial Revolution in 1750, we've seen levels of carbon dioxide rise at a great rate in the atmosphere, and that's through the burning of fossil fuels such as oil, gas and coal. Now, many students will have heard about how that carbon dioxide in the atmosphere is causing climate change, but up to a third of that carbon dioxide is being absorbed by our oceans. Now, that is of course a good thing in many ways, because if that were still in the atmosphere, we'd be experiencing even greater levels of global warming. Absorbing into the ocean, unfortunately, it creates another change which we call ocean acidification. So the carbon dioxide absorbing the ocean, dissolving in there, dissociating, and that chemical change is causing the pH of the ocean, that's a measure of acidity, to decrease. Now, in about 1750, the average pH of the ocean was about 8.2, and now it's about 8.1. So that's a 0.1 decrease in pH, and that represents about a 30% increase in the acidity of the ocean. You can just hear the plane behind me heading back to Longyearbyen. So that's a big goodbye. And the next flight that comes in to Ny-Ålesund is very sadly the flight that will take us homewards. But back to ocean acidification. So we have this chemical change where we're seeing the pH of the ocean, and pH is our measure of acidity, change over time. Now, our first activity is to look at whether we can replicate the passing of carbon dioxide through water and what effect that might have on its pH. So for this activity, you need a few things. You need some water in a vessel. A cup will do. You need a straw. This is a metal straw. Please try and cut back on your single-use plastics. So if you are using other types of straws, paper is good, or perhaps at a push reusable plastic straws. Do try and have, for hygiene reasons, sort of one per student, so you're not sharing straws, is a good tip. Sorry there. And then we have a pH meter, and that is measuring the acidity of the water. And we have this in a buffering solution at the moment, just to keep it happy. And the pH here is measuring 7.64, but I'm just going to get those 7.64, and we're just going to take those and open this up. Hold those carefully between two fingers, and get that into my water here. And what we're going to look at is if I blow through this water, how is the pH going to change? We're looking at a couple of things. We're looking at prediction here. From what I know about the behavior of carbon dioxide and its impact on the water, what do I predict will happen to the pH here? I'm just going to swirl this around, and what that hopefully will do is speed up the rate at which the pH meter accurately measures the pH of the water here. It's dropping now. On a previous test, we had a pH of 7.02 as our starting point. Then what I'm going to do is, for 2 minutes, I'm going to blow carbon dioxide. When I exhale, because of respiration, there's more carbon dioxide in my breath. I'm going to blow through here for a couple of minutes. I'm going to see if the pH changes at all. Now, when you are blowing through your mini ocean, a couple of things to remember. Do not blow too hard, because then you will splash the water everywhere, especially if you've got a small cup or quite a full cup. The second thing is to make sure that you take turns, so don't pass out by blowing as long as you can. So do take turns every 10 to 15 seconds. So you can do this in a group, maybe between 2 and 4 of you. So remembering not to blow too hard, each have your own straw, and then also taking it in turns every 15 seconds or so. So let's look at where we're settling on our pH. I'm going to put my straw down and pick up my pH meter, and I'll show that to the camera. What have we got on there, Ellie? Because it's sort of, I know it's flipping around 7.25, 7.3. What have we got?
Is 7.29.
7.29.
7.28.
Okay.
2829.
Brilliant. So what we'll do is we'll put those back into my solution there. pH probes like to be kept in water. And then we're going to start by blowing through the water, and we'll see how we get on and see what happens. And just thinking in your classroom, maybe you're doing this alongside us. maybe you are just following what we're doing here in the Arctic. In terms of measuring the change in pH, there are a number of different ways you can do that. You can use an electronic pH meter if you have one of those to hand. You can also use a litmus paper or some other form of indicator, so that will give you a different color depending on the pH. You can do a homemade pH indicator, such as making red cabbage water. It is quite stinky, but it is an effective and natural way of looking at how the pH of a liquid is changing. And Ellie will time me on my 2 minutes, and we might do 2 sets of 2 minutes here. So whenever you're ready, Ellie, and then let me know.
Okay, 3, 2, 1, go. 30 seconds. One minute. One minute 30. Five, four, three, two, one, and stop.
Oh, there we go. So hopefully everyone's had a couple of minutes, have a go, and then I'm going to put the pH meter back in here. You can get pH meters for about 40 or 50 pounds, I think, if you're interested in getting one for your school. So we're just going to see what the changes are here. At the moment, if we are led to believe, in fact, the pH has gone up so far in here, but I think that's the difference between the buffering solution over here and the solution and the water we've had and we've bubbled through here. So we are at 7.29 at the moment, which is where we started, 7.28, and we'll see if that drops any further. Now, what we're looking at to see is we've put carbon dioxide through our mini ocean, of course, at a much faster rate than is happening with the ocean as a whole, but with 30% of human generated carbon emissions are being absorbed by the ocean, it is a huge amount going into the ocean as well. And we've got this dropping, we're down to 7.2 already, so we're nearly coming up to 0.1 of a unit of pH, and 7.19, 7.18, 0.1 of a unit. That is the equivalent to the pH change that we have had since the beginning of the Industrial Revolution in 1750. The predictions are that by the end of this century, by 2100, we're going to see a further 0.4 of a unit decrease in pH down to about 7.7. There are various models, and of course we can come on later to those things that we can do about it. So, how are we getting on? If I lift this up, what's that steady on, Ellie?
7.07. 7.08. 0708.
Okay, 708. So that's a 0.2. Wow. Okay. Great. Let's try for 2 more minutes. Whenever you're ready. I know it's incredibly exciting to watch someone blowing bubbles in the Arctic, but hopefully you're joining in the classroom too. Which camera are we on? Perfect.
3, 2, 1, go. And 30 seconds.
And now for some pictures of Arctic wildlife.
One minute. One 30. Three, two, one, and
Great. So what were we on last time? 7.08.
oh, 08, yeah.
Perfect. So I wonder whether in the class you had predicted this fall in pH as we increased the amount of carbon dioxide that goes through our mini oceans. And so I'm just seeing here we are still having to fall from the 7.2s all the way down, we'll see, to 7.08 and see if that goes any further down. So we are 7.16 at the moment, and I think it might just take a wee bit of time to get down to where the levels are in terms of the water that we have blown through. While we wait for that to happen, we're going to consider what some of the impacts might be on the marine habitat, on the marine ecosystem. Now, what we've got in our second live investigation, and this is where we're really observing, is we have got pieces of chalk. And the reasons why we have pieces of chalk is that there are many marine organisms that have a structure or skeleton that is made out of calcium carbonate, and that's the same mineral that chalk is made from. Now, when you have ocean acidification, you find that there are fewer carbonate ions available, so carbonate building blocks available for creatures such as shellfish, so mussels and oysters. Coral make their structures out of calcium carbonate, and also some of the smaller zooplankton, and that is a type of organism like the pteropod. Other organisms are also affected by changes in ocean pH, and they find that change in pH really impedes their metabolism. So you have the copepod, the bottom of the food chain animals, who respond pretty poorly to rapid increases in pH. That was an experiment done in the Arctic also about sort of 6-7 years ago. So what we're seeing is that pH has an impact on the metabolism of these creatures when they put into future scenarios of pH. And also even now we're seeing a variety of animals that are being affected, especially in the larval stage. And that is because if you think about it, if your blood became 30% more acidic, then you will be put straight into an ambulance and rushed to A&E. Marine creatures surrounded by this environment have to use a lot of energy to keep their body systems going, and if the environment changes, they're using more energy either to create their structures or just to keep their body systems going. Now, if they're doing that, then they have less energy for other things such as reproduction and growth. So, this has decided to switch itself off, so we'll let that come up. And then we'll do our second observation, which we're going to put chalk into an acidic substance. In this case, we're going to use vinegar, malt vinegar, and we're going to observe what's happening. Just before we do that, Ellie, we have a final readout of 6.87. Glad to see that we are, although we had a higher starting point this time, glad to see that we are at least consistent as we had 6.87 this morning as well. I'm just going to move this to one side. And also welcoming on a few other schools. We have White House Middle School. Hi. We have Warwick Academy in Bermuda. Big hello to you guys. We have Riverside Public School, we've had to say hello to earlier. And is that Colliston Grammar School down in Devon. A big hi to you and all the students there. For this next stage, if I just pull this over, what we're really doing is we're just observing what happens. I'm going to get a few more pieces of chalk out just to have a blue one, a brown one, and a bit of a green one as well. The reason why I'm breaking the chalk is sometimes modern chalk, they put a coating on the outside, and if you break it, you're basically making sure that the sort of chalk itself is exposed to the vinegar. Put that chalk to one side and then take the vinegar, and then we'll have a look to see what happens. Oh, a bit of a whiff, and I'll hold this up in a bit if that's okay. Just easier to pour on the table. Which camera would you like me to hold it up to, Ellie? This one? I'll just hold it up. Give it a bit of a shake, hold it up like that. Is there a... I think around this side I've got some action. So haven't it? You can see anything happening there? Gentle fizzing, I'm hoping for.
Very faint.
Very gentle fizzing. Shall I get up and hold it right by the camera?
Yeah.
Yes? I'm going to give you a good whiff of a fish and chip shop up here in the Arctic.
There you go, yeah.
Let me turn that around.
There we go.
Tip it.
That's perfect.
So what we can see here, through a chemical reaction, the chalk is essentially dissolving in the vinegar. And we should have that chemical equation written up on our ocean acidification fact sheet and in some of the background information to this. Now, there are some instances, I'm trying to sit back down now, you've seen that. There are some instances already of sea life, the shells dissolving, not forming properly in the current ocean pH. But the impact that we're really seeing documented in terms of economic impact we're seeing is, for instance, the larval stage of the oyster fisheries in Washington State in the US, very, very badly affected by ocean acidification already. So we're seeing those kind of impacts from the changing chemistry of the ocean affecting the larval stage of these shellfish. And we will talk in a bit more, probably based on some of the questions that come through, what are the impacts, what does it mean for our society, for the economy, those types of things. This sort of secondary effect of increased atmospheric climate carbon dioxide and how that is coming into the ocean, changing its chemistry and affecting the life there. And first question we have is from Asmir from Riverside Public School in Canada, asking what is a natural pH balance that we as humans should maintain in our oceans. It's a great question, Asmir. The pH before the Industrial Revolution was on average 8.2. Of course, across the ocean you have variation of pH, so it's not the same pH everywhere, but we're looking at an average ocean pH. But it is pretty stable around sort of 8.1, 8.2, that kind of figure. Now, it's really looking at change that is a problem. So some marine species may live in an area where there's a lot of fresh water input, and we've seen the fresh water here in the Arctic with a pH of about 7.2, 7.28, I think the sample we just had just now. So if you're living next to a glacier and that melts into the water, then of course you're going to get a lower pH. What the important thing is that whatever pH you're adapted to, that shouldn't change too rapidly. What's happening at the moment is because of the amount of carbon dioxide in the atmosphere, the natural processes aren't able to stabilize the chemistry of the ocean. And in fact, the chemistry of the ocean, the pH is changing more rapidly now than at any other point in the past 300 million years. And it's that rate of change that is posing problems for marine life. So we may have come across a term called evolution and adaptation. So how organisms can change over generations through populations to adapt to the environmental circumstances. Now, if evolution can't cope at the right pace to keep up with environmental change, then that's where you see some species and individuals will die off, and there'll be more problems for those living things. So it's a rate of change we're really having problems with at the moment. And so what pH balance should there be is that change should be as low as possible, and that means fewer carbon emissions. Second question from Asmir from Riverside Public School. We noticed that when we analysed our graph, there was a drop in ocean pH between 1997 and 2001, yet carbon dioxide kept climbing. Why is that? Well, a drop in pH is actually an increase in acidity. So that is exactly what we would reckon should happen. That if you have the pH falling, that is because of increased carbon dioxide. That's exactly what we saw in the first investigation we did. We added carbon dioxide and we saw a drop in pH. If you mean a drop in acidity, we can come back to that. Please repost the question on the live chat. But to answer that question as written, that would be the reason. Warwick Academy in Bermuda. Hi. What is the main cause of ocean acidification? The driver for ocean acidification is carbon dioxide in the atmosphere. That's through burning fossil fuels, and some of the main causes of that are how we travel, how we eat, and how we live. So if you're looking to decrease, do think about those three areas: how you can decrease your carbon emissions when traveling, when eating, and that's moving to a plant-based diet, and also across other aspects of your life in terms of your consumption, in terms of your electricity use, and that kind of thing. Does the ocean temperature change in the Arctic? And that's from Warwick Academy. Certainly the Arctic Ocean is warming, and the Arctic region is warming faster than any other region on the planet. So I haven't studied the sea surface temperature recently and the changes over this year, but for the past 30 days in Svalbard, in this region of Svalbard, it has been 6.8 degrees warmer than the average, and it certainly feels from my short experience of being in the Arctic that it is getting warmer. People who have been here longer have been noticing how there is less sea ice in the fjord. Often at this time of year, you would have seen sea ice across the whole fjord, and our sampling would have been very difficult. And also the glaciers in this region have been in retreat. Which animals are worst affected by ocean acidification? I don't know who this question is coming through from. Great question though. And really those animals that we're seeing most affected are those with a carbonate structure or skeleton. So we've got oysters. We've mentioned that specific case study with the Washington State oyster fisheries on the west coast of the US. We also have coral reefs which grow their amazing structures from calcium carbonate, and then some of the zooplankton that we find up here. So especially the pteropod, species of pteropod which have a calcium carbonate structure as well. So those are the ones that are really affected because ocean acidification causing a greater scarcity of carbonate ions in the ocean. Do we understand that even the addition of fresh water decreases pH? We do understand that the addition of fresh water decreases pH, and I'm wondering whether that is you would like a clarification on how that takes place, or whether we should mention that again. So the pH of fresh water varies. It can be depending on the mineral composition of the ground and the earth it's coming through, anywhere between pH sort of 4 and pH 9. So fresh water has a variable pH because there aren't those processes that keep it steady. So that's one thing to take into account already. But say our fresh water, we're positing or putting it that it's below the pH is below the pH of seawater at 8.1. So say it's about around 7, for instance. When we have those areas where there is fresh water input, such as at the head of the fjord here, or in a river mouth area in other areas of the world, then you're going to have variable pH, and you'll find that species are adapted to that range. Those species that are adapted to ranges, and it's even true in the Arctic, if you have a bit of plankton that travels up and down a couple of hundred meters, then it is going to be more resilient to future changes because it's experiencing that greater range during its life. So yes, we do understand that fresh water does impact pH, and also that those species that experience a greater range of pH during their normal life will be able to, or could be more able to be resilient to future changes of pH. Next question we've got coming up, we have, what does acidification do to
biodiversity and is it bad? It puts a lot of pressure. So in terms of biodiversity, it puts a lot of pressure on a number of species. In particular, if we focus on an ecosystem which is very high in biodiversity, such as the coral reef, coral reefs will find it harder to grow and may even dissolve in future scenarios of pH that we might find towards the end of the century. And so, because the coral reef supports 25% of all marine species, that is incredibly bad for biodiversity. But there are a number of species that are and will feel the pressure of decreasing pH, of increasing acidity. And is it bad? It's bad in a number of ways. If you affect the balance of an ecosystem, it will stop providing the services that you are used to, and that has a negative impact on society and the economy. For instance, there are over 1 billion people who rely on fish for their primary source of protein. If they don't have those small animals like plankton to eat anymore, then those fish stocks will start to dwindle even more, and that impacts those people. And if we have, for instance, fewer coral reefs because they become more fragile or aren't growing as fast and can't stand up to other impacts and stresses, then they, for instance, protect vast swathes of coastline from the full force of the ocean, and that will be an additional impact on society. Let's next up Ariana from Riverside Public School. What laws can we put in place to ensure that ocean acidification stops? Ariana, that is a great question. And so the laws that you are looking at are those which limit carbon emissions. So laws you could put in place, everything from where do we start? I think the first thing, I think the interesting thing is the government positions on what threat climate change and carbon emissions pose to society. And it's great to have seen the UK government declaring an environmental emergency last week. So it is looking at how we view this, and then the laws will come out of that. So, for instance, you can have laws that affect agriculture. You can have laws that affect energy production. You can have laws that affect car manufacture. You can ban, for instance, the internal combustion engine in every car manufactured from 2030 onwards. You can put in other mechanisms such as tax breaks for alternatives that use fewer fossil fuels, and you can also do what we call taxing externalities. So if you are using a product that has an overall negative impact on the environment, that is taxed at a higher rate. So there are a variety of different mechanisms that governments can use. You could have a law, for instance, that requires every single new build, or certainly every single commercial and industrial new build, to have a green roof or solar panels. So there are lots of different mechanisms that we can do, and we can think about those. And more importantly, I think we need to have that general agreement that we are living during a time of environmental emergency, and that we need swift action on a lot of fronts to reduce our impact on the planet and reduce, especially in this case, reducing our impact on the oceans. What's the biggest problem for the oceans? Plastic or climate or acidification or habitat loss? Which is most urgent? One way of dodging this question would be to say that the ocean is facing what is called a multiple stress environment, so that if one of these things were happening, ecosystems might be able to stand up for themselves and be resilient. But because there's plastic and ocean warming and acidification and habitat loss, they can't stand up to all of them. But let's pick up a couple, and in fact the last three are pretty connected. They're all to do with carbon. So climate change and ocean warming driven by increased carbon emissions in the atmosphere. Acidification is driven by those same processes of burning more fossil fuels. Habitat loss is in fact reducing our carbon stores, so that there is a lot of carbon which is stored in places such as the rainforest or seagrass meadows or mangroves. And when we reduce those stores, we're releasing more carbon into the atmosphere, and also we're not taking that carbon out. So we would be wonderful to have more mangrove, more seagrass meadows, more rainforest and other forests um, on the planet, as well as reducing our carbon footprint as well. And there are carbon footprint calculators that you can use online. We'll post one on the live chat where you can look at where your how big your impact is, and then it should give you some idea about how you can start to reduce it, so your footprint it becomes smaller and we have a wonderful future. Very sadly, but on that note, is sadly we're coming to the end of this live broadcast. Really important question, both on what we can do and where some of the problems are. Thank you for taking the time to find out more about ocean acidification. But as our sessions are titled today, it is all about high CO2 and what we can do to reduce it and what impact it is having on the Arctic. And that is the Arctic Ocean as well. So thank you so much for being part of this. It's been wonderful to have you. Do join us again in about an hour's time when we will have PhD student and polar oceanographer Hannah Green join us. But until then, it's a big goodbye from the Arctic. Bye bye.